You've already learned everything there needs to know about hypothesis testing regarding a population proportion P, including assumptions, forming hypotheses, calculating the test statistic, and of course, making a decision by either the critical value or p-value method. Our focus is logically now going to shift from proportions to means. So we, of course, are going to need to know how to run a full hypothesis test and everything that goes along with it regarding a population mean. Similar to when we had to estimate a population mean using a confidence interval, we utilized the t distribution rather than the standard normal z distribution. We're going to be doing the same thing here. So therefore, we specifically call hypothesis testing for means a t-test. Let's begin with our assumptions. So our first assumption should be very familiar to you. We do need an SRS. That's the same across both tests, proportions or means. Remember, we do need a normality assumption. If you go back to previous material, the normality assumption for any type of mean inference is always going to be either a normal population, a population that is normal, or if it's not, of course, our very famous n is greater than or equal to 30 that comes from the central limit theorem. Lastly, our sample values must be independent of one another. That is also similar to the proportion test. You've already had some training with the null and alternative hypothesis. Remember, that is always step one of a hypothesis test. Just remember that we're no longer using the p, population proportion p, as our variable because we're now dealing with means. So the population mean, of course, is mu. And we usually refer to the number that takes the value of mu, our population mean, as mu sub 0. All the other rules stay the same. The null hypothesis, of course, is a statement of equality right here, and we're dealing with two left or right-tailed tests depending on the wording of our problem that we're facing. We, of course, have to find our level of significance, alpha. That will be no different than any other test that you run here or if you're going on to Stat 2. Alpha is always that level of significance, and it will be provided to you as 1, 5, or usually 10%. Our first computation in a hypothesis test comes in the form of our test statistic. You'll notice that the formula is obviously much different than the test statistic for population proportions, but it's in the same form or format, right? So just as a reminder, when we were doing sampling distributions of sample means, we were asked to standardize some value, and we standardized it into a value of z, which was x bar minus mu over sigma divided by root n. So you'll notice that our test statistic for our t-test is just an adaptation of this same formula. We, of course, are going to be using t instead of z because this is a t-test. And we're going to be using the sample standard deviation instead of sigma. Recall that we use the sample standard deviation s because sigma is unknown in any t-related inference technique. Let's look at an example and complete the initial steps of our hypothesis test for a population mean. It says the average 1 ounce chocolate chip cookie contains 110 calories. A random sample of 15 different brands of cookies resulted in the following calorie amounts. The 5% significance level. Is there sufficient evidence that the average caloric content is greater than 110 calories? Assume the average calorie amounts are normally distributed. Starting with our assumptions, our first important thing is our SRS, which you can see is right here. So that's all good. The second one is our normality assumption. Remember that by the central limit theorem, we're normally looking for n is greater than or equal to 30, but right away you're going to see that that isn't happening. So there has to be some other thing that is true to make this normal. We really can't use these methods. And if you recall, if the population is normal, then we're good to go. And you can see that the calorie amounts here, the cookie calorie amounts, are normally distributed. That's saying that the population is normal. So as usual, if the population is normal, then we know that the sampling distribution is normal. Lastly, we're looking for independence among the calorie amounts, and that is true. Every cookie has its unique calorie amount, and it doesn't have any probabilistic effect on each other. Therefore, we can go ahead and use our hypothesis tests. All right, we need a null and alternative here. So we have H naught, H1. Remember, we are now in the world of means. So if you want to take a peek right here, just as a reminder, because we did do a preview of how to form hypotheses in a different video, but now we just have to make that mental change. So now we're dealing with a statement of equality with the population mean mu. We're looking for some type of claim about the population, and a great claim here is, you can see, average 1 ounce chocolate chip cookie, 110 calories. All right, and the alternative, we're looking for some language that helps us with whether this is a left, right, or two-tailed test. You can immediately pick out, hopefully, in the question in the statement, the word greater than 110. So that means we are here with the null and alternative. And of course, our significance level was also given to us as 0.05. That will come in later when we're decision making. So the last step up here that's already introduced before we get to the remaining steps is, of course, our test statistic. That is going to be a value of t. We'll say t sub 0 is equal to x bar minus u sub 0 over s divided by root n. If we go and look at this formula, you're going to see that we do have some things. For example, in the numerator, we definitely have this right here, which is going to be 110. And we definitely have the sample size, which is going to be 15. But you'll see that x bar and s aren't really given to you in the original problem. I know you're looking at it right here, but it's not really given in the original problem, so it would have to be calculated from our data. This would be a pretty straightforward thing to do, though. You could use StatCrunch, Pearson's built-in software. You could use your calculator, and you could also use a online calculator for calculating sample standard deviation. But either way, just remember that this might not be given in homework problems, and you might have to find it. On the exam, though, since we don't have access to a lot of that stuff, I would give you the sample standard deviation. Maybe not the mean, just because that's easy to compute from here, but I would have to give you that sample standard deviation. Okay, so back to the task at hand. We do know what x bar is, 137.3. We're going to subtract our mu sub 0, which is our value that is in our null and alternative hypothesis. We have s now, 24.1, and we're going to divide by the square root of 15. When we do so, we're going to get a test statistic of approximately 4.39. Okay, now that we've exhausted all the steps up here, and you can see that the flow is very similar to the proportion tests, we now need to go to the decision-making stage and what that entails. So for mean tests, you do have the option of the critical value method and the p-value method. I will explain later why the p-value method can be a bit challenging to pull off with t-distributions. So we'll start with the critical value method, which is pretty straightforward. You're going to see here that this graphic is very similar to the graphic that was for proportion z-tests. So instead of having plus or minus z alpha over 2 minus z sub alpha and positive z sub alpha as our critical value options for the different tailed tests, now we're just replacing the z with the t. So you can clearly see across the board here, it's identical by just changing the variables. One thing we are going to take note of here is, because we're dealing with t, we're back in the world of degrees of freedom. So when we go to the t-table to pick our critical values, when we did so for the proportion test, we were on the bottom row because we were dealing with z. Now we're dealing with t's, so that means our degrees of freedom are going to come in, and we're going to be using all of the values in the body of the table in order to find our critical value. And lastly, all of the regions are set up in exactly the same way as the proportion z-test. So as we do this in a second, it's going to feel like there's really nothing different other than trying to locate the proper critical value based on the degrees of freedom. Okay, so just like last time, we're going to draw our curve. Okay, and in that curve, we are going to have to find our critical value. So writing critical value, and I say value because this is clearly going to be a right-tailed test that we're dealing with right here. So our critical value is going to be positive t sub alpha. Now, alpha in this problem is clearly 0.05, so not a lot of work so far. We're looking at t sub 0.05. Now, to be clear, again, if you go back to the t-table and you look up 0.05, for the proportion tests, we would have had to go all the way to the bottom and pick this number. We cannot do that anymore. That is only for a z critical value. We now need to find the proper degrees of freedom to find the proper t critical value. So what would be the degrees of freedom for this problem? It'd be n minus 1 as usual, so that's 15 minus 1, which is 14. If we go over to the t-table, we're going to go to 14 and 0.05, meet in the middle at 1.761. Remembering that we are bringing the signage over. That allows us to go to our t-distribution and label 1.761 on the graph. Remember, 0 being in the middle. In a right-tailed test, we always reject in the right tail. It's a nice little handy way to remember that, right? So we draw our little rejection region and do not reject in the rest of the curve. Same as our flow for last time when we were dealing with the proportion tests. This 4.39, which is basically being in your back pocket this whole time while you've been constructing all of this information right here, can now be put into our curve. So this 4.39 would fall somewhere over here, which is clearly in the rejection region. Therefore, we would choose in this problem to reject H naught and side with the alternative. So we basically believe that this is going to be greater than 110 calories. Okay, so we have our decision, reject H naught. Remember our interpret statement, same thing for t-tests. At the 5% significance level, the data does provide, because we rejected H naught, sufficient evidence that, and then we just have to reiterate that alternative hypothesis no matter what. So it looks like that the cookies have a calorie, we'll say count of greater than 110 calories. And that puts a bow on it. All right, let's look at a few more examples. It says, a national magazine claims that the average student watches less television than the general public. The national average is typically 29.4 hours per week. A sample of 30 college students has a mean of 28.4 hours and a standard deviation of 3. At the 10% significance level, do the data provide evidence to conclude that the mean time watching television by college students is less than 29.4 hours a week? All right, so let's just assume that all the requirements and stuff are met. Let's just jump right into this. So we have null and alternative. We have a statement of equality for the population mean. It looks like the sample yields of 30 yields this mean and this standard deviation. Therefore, the population claim must be this mean, 29.4 hours per week. Okay, the alternative is going to be a statement of less than, greater than, or not equal to. We're looking for a keyword. I spy less, so we have less than 29.4 hours per week. Alpha was provided as 0.10, 10% significance. We can calculate our test statistic. Remember, this is going to be t sub 0, x bar minus mu over s divided by root n. All of these things are given to us. We have 28.4 for our sample mean. We have 29.4 for our population mean. Our standard deviation was given as 3, and we have a sample size of 30. Therefore, when we do this calculation, we're going to get around negative 1.83. Continuing with the critical value method. So we have our distribution here, t-distribution. Our critical value is going to be equal to, in a less than left-tailed test, that's always going to be negative t sub alpha, which is going to be negative t sub 0.10 right here. And we need that degrees of freedom in order to make this work. So we have the degrees of freedom is equal to 30 minus 1, which is 29. So we go over to our t-table. We're finding 29, which is here, and we're looking for 0.10, which is here. We meet in the middle, and it looks like we're at 1.311. So we go back and we say, okay, we got to bring the negative over, get 1.311, and we go to our distribution and we place that number there. Remember, in a left-tailed test, just in case you make a mental error, you're going to have your critical value in the left tail. So if you don't bring this negative over and you end up over here, then that's not right. It already doesn't make sense. So just be aware of that. Again, if you have a left-tailed test, you reject in the left tail. So you're rejecting over here and H naught, and you do not reject H naught over here. We then can take our test statistic, we can place it where it belongs in our number line of things on our t-distribution, and negative 1.83 would fall just about right there. So our decision would clearly be to reject H naught. Okay, so here's your interpretation. At the 10% significance level, the data does provide, because we rejected, sufficient evidence that the mean time watching TV by college students is less than 29.4 hours per week. Last example here for the critical value method. In 2001, the average passenger vehicle was driven 10.3 thousand miles. As reported by the U.S. Federal Highway Administration, a random sample of 500 passenger vehicles had a mean of 9.85 thousand miles. Statistician believes the Highway Administration could be incorrect in their initial estimates. The 5% significance level, do the data provide evidence to conclude that the mean mileage differs from 10.3 thousand miles? Assume S equals 6. Okay, let's jump right into the known alternative. Again, let's assume the requirements are met just to speed up the video here. We have a statement of equality of the population mean. If you look, we do have a sample, random sample of 500 passenger vehicles, which yields a mean of 9.85. That implies that our 10.3 in thousands will represent our population mean. Just note that you could write out 10.3 thousand numerically, but it's much easier in terms of calculations to work with smaller numbers, so that's why it was chosen to use the word thousand here. We're not going to change that, though. Our statement for our alternative hypothesis usually comes from keywords. If you read through this again, there aren't going to be any words insinuating less or greater than, but they really use incorrect and differs, which are definitely insinuating that this is going to be a two-tailed, not equal to hypothesis test. Alpha is given as 0.05. Our test statistic is going to end up being x bar, which is going to be 9.85, minus our mu, 10.3, over our standard deviation, which was given at the end of the problem, of 6, divided by the square root of our sample, which is pretty large, 500 passengers. If we do this computation, we're going to get negative 1.68. Since we're doing the critical value method, we basically just want to pop this in our back pocket and move on to our critical values and our graph. So we're looking at crit value. We'll say crit values this time because it's going to be plus or minus t alpha over 2. So remember, alpha is 0.05, which means alpha over 2 is going to be 0.05 over 2, which is 0.025. So therefore, we're going to have plus or minus t sub 0.025 at degrees of freedom equal to 500 minus 1, which is 499. Looking this value up is a little tricky. If you go to the t-table, we're going to be at the 0.025, so we're going to be in this right here. But if we go down to the values that we want, you're going to see that there is going to be no 499 anywhere. So as I mentioned before, whenever you don't know, you want to round down. So we're going to be using df equals 100 for this, which means that we're going to end up with 1.984 from the 0.025 column. So I'm just going to make a note here. Use df equals 100. Okay, so we end up with that value that we found, 1.984. Remember, it's both positive and negative because there are two critical values. In a two-tailed test, we reject in the two tails. So we reject H0 over here and over here. And we fail to reject in the middle. We then take the negative 1.68 out of our back pockets. We place it in the number line of things on our t-distribution, and we get it located about right there, right? So you can clearly see that that is in the middle region. Therefore, our decision is going to be to do not reject H0. Okay, just remember, when you fail to reject H0, that means you're basically siding with the null hypothesis, and you're saying that the alternative is basically untrue. And lastly, here's our interpret statement. We can say at the 5% significance level, the data does not provide sufficient evidence because we fail to reject H0, that the mean mileage of the average passenger vehicle differs from 10.3 thousand miles. Just be aware here that not everybody's really going to use this word per se. You could have said is not equal to 10.3 thousand miles, just like the sign here. You could have said that it's not 10.3 thousand miles. I've seen students say it's incorrect. All of these are correct answers. I'm not looking for perfection when it comes to restating the alternative, but it basically does have to say what's here. So you've seen examples of a left, right, and two-tailed tests when testing population means with the critical value method. Now, we also have the p-value method, and just as mentioned with the proportion tests, the p-value method is the most popular in the real world. But there's a reason for that, because most of what is done by hand here by us is done using technology, and the p-value method is much easier to quickly come up with a conclusion than finding critical values and making regions of rejection and all of that. The problem is, if we don't have technology, the p-value method is a very challenging path to go when it comes to t-tests. Why is that? Well, you know, in the z-table, all of these wonderful areas for the p-value are located in the body of the table. It's pretty quick to find based on just a typical normal distribution. If you go to the t-table, though, look at this. There are no areas in the body of the table. They're all critical values. As a matter of fact, the only areas in here are actually on this top row, and there's only a handful of them that are actually up here. It turns out using these areas in order to do the p-value method for the t-test is just more trouble than it is good for students. So in most cases, we try to just avoid that. So what does that mean for us? Let's look at an example, and I can give you some pointers on where to go in a scenario where you need a p-value for a t-test. It says Duracell manufactures batteries that the CEO claims will last an average of 300 hours under normal use. A researcher randomly selected 20 batteries from production line and tested these batteries. The mean life, 273 hours. Assuming that the batteries are normally distributed and known to have a standard deviation of 50 hours, do we have enough evidence at the 1% level to suggest that the claim of an average lifetime of 300 hours is incorrect? Okay, let's follow this as the typical hypothesis test. So basically do the first 3 steps. And then when we get to the decision-making step, then I'll talk more about what needs to be done. So we're looking at, go back to orange here. We have the null and alternative. We have mu being with a statement of equality. You can see that we have a sample here of 20 batteries with a mean of 273. So the claim actually is 300 hours of use. And when we go to do the alternative, this word is just popping out at me here, implying that we have a two-tailed test. So not equal to. Alpha is 0.01. We also have our test statistic here, which is going to be our 273, which we've identified at x bar, minus 300, which is mu. Our sample standard deviation looks like is 50, and we're going to divide by the square root of 20 for the batteries. That is going to give us around negative 2.41 as our test statistic. As I mentioned before, this is when we run into issues. So we cannot look up negative 2.41 in the z table because remember, if you recall when we were talking about t-distributions, some of the earlier lessons, t-distributions are flatter distributions with higher tails. They don't have the same area distribution as the standard normal distribution, except at the highest sample sizes. So this table's out. If you go to the t-table, there are no areas in here to directly find the area that is related to negative 2.41. And as I mentioned before, this process using these area values is just more trouble than it's worth. Therefore, we do have some options at our disposal, but they will always involve technology. So what does that mean for you guys? When it comes to exams, then almost all t-tests are going to basically use the critical value method. That's important for you to remember, and I will mention that later on down the line. So, but that doesn't exclude homework. And when you're doing the homework and you need a way to actually find the p-value in a t-test, then what can you do? Well, just like some of the previous material when we were trying to find the sample standard deviation online, there is something called a p-value calculator. And what does that require? All that you do is you plug in the test statistic t into the website, and often sometimes the degrees of freedom, which in this case would be 50 minus 1 is 49, and whether it's a left, right, or two-tailed test. And they'll just spit out the p-value for you, and then you'll be able to write it wherever it's going to be in the homework. Another option is to use StatCrunch. So just as an example, I happen to have a piece of it here. So this is typical StatCrunch output for a t-test. You can see, actually, it's pretty cool. The t-stat is right there, which is now verified as negative 2.41. So I guess hypothetically you wouldn't need to do this part if you were running the StatCrunch output. But the p-value is clearly noted here as 0.026. So if you recall from our proportion tests, we always ask ourselves, is p less than or equal to alpha? So in this case, p is 0.026 and alpha is 0.01. And clearly that is not true. And when it's not true, we do not reject H naught. Okay, and that's going to be basically our decision that we got from a p-value, either from a calculator online, from StatCrunch, and technically some of your calculators do this as well. You just have to do a little research to figure that out. But again, just to reiterate, on exams, which is what most students are more concerned with, I'm going to focus on the critical value method for t-tests, which means it's kind of logical that I'll probably shift using the p-value method for proportion z-test, just because you need to know both of them, and that's really the best way to do it.